So we're going to talk about the capital asset pricing model, which is what we did in Project 4. So first I want to just talk for a second about risk. We already talked about it a little bit, but risk is getting something other than what you expected to get. So it can be higher than what you expected to get, or it can be lower than what you expected to get. We're not usually unhappy about the ones that are higher returns than we expect to get. But either way, it's risk. So there are two ways that we generally look at an asset's risk. One is in isolation, so looking at the asset by itself in isolation, only that asset. And then the other is looking at the risk in a portfolio context. So looking at an asset's risk by itself, we usually look at standard deviation. So standard deviation tells us the risk of the individual asset and that's the asset's total risk. Then we look at the risk of an asset in a portfolio. And in a portfolio context, we have two different types of risk: unsystematic risk and systematic risk. Systematic risk is also known as market risk, and it is the risk of the security as it relates to the market portfolio. And this is the risk that, according to the capital asset pricing model, is rewarded. Unsystematic, so I'll talk about that a little bit more in a few minutes. Unsystematic risk is also known as diversifiable risk. This risk is not rewarded, and the reason for that is that we can diversify it away. So by selecting a portfolio where the assets aren't perfectly positively correlated with one another, then we can reduce the risk of our portfolio by eliminating most of the diversifiable risk. So therefore this risk is not rewarded. So total risk is systematic plus unsystematic risk. We usually use standard deviation to measure total risk, and we usually use beta to measure systematic risk. The relevant risk in the context of a portfolio is the risk that a security adds to that portfolio. So when we look at the distribution of returns, we can see that we reduce the standard deviation. So this portfolio of 20 stocks here has a lower standard deviation, right, than this portfolio of, I'm trying to do a pin here, than this portfolio of one stock or two stocks. So the standard deviation is smaller for a large portfolio than for an individual stock, even two stocks. The more stocks that you add to the portfolio, the more unsystematic risk you get rid of until you get to around somewhere between 30 and 40 stocks, and then after that you're not getting very much risk reduction for the cost of adding additional stocks in the portfolio. But when you add those first few, you can reduce your risk a lot. You can't get rid of this systematic risk. That's going to stay. Doesn't matter what you do. You can't get rid of that systematic risk because that's the risk of investing in the stock market at all. Or investing, let me say, in risky securities at all. So the implications are, as the number of assets in a portfolio increases, the variance, or as I said, standard deviation, decreases and approaches the average covariance. So the variance will decrease and approach the average covariance between the assets of the portfolio. As more assets are added, each new asset has a similar risk-reducing impact on the portfolio, but you don't get very much diversification benefit once you hit 30, 35, 40 stocks. The standard deviation of portfolio falls very slowly after that. So an asset's covariance with all the other assets in the portfolio is the only measure of risk that's relevant, because we aren't going to hold the assets in isolation, so we're not going to hold them by themselves. So we don't worry about variance or standard deviation for individual assets. We worry about the contribution of the variance or standard deviation of that asset to the variance or standard deviation of the portfolio, and that we can look at the correlation coefficient to determine, or rather we can look at the correlation coefficient to determine how much risk we're going to be adding if we add that asset to the portfolio. So by forming well-diversified portfolios, we can eliminate about half the riskiness of owning an individual stock. Okay, so let's switch gears and go to beta. So we talked about beta in the pre-lecture, and I talked to you about it in class a few times. It's the measure of systematic risk. You also study it in 3312 and very much so, very intensely in 3318 investments. It's a measure of the systematic risk of an asset or portfolio, and that's the slope of the regression line between an individual security's return or a portfolio's return, as you notice because you did it on your portfolio, and the return on the market. So I don't need to tell you how they're calculated because you've already done it. You ran a regression of the security return on the return on the market. And I'm going to talk about that specific regression in a little bit here. Most stocks have a beta of between 0.5 and 1.5. Some of you were getting negative betas, and I had you go back and make sure that your dates lined up. If your dates lined up, you probably didn't get anything with a negative beta. Most analysts use the S&P 500 to find the market return. They usually use 5 years of monthly returns to establish the regression line. And we're using 5 years of monthly returns mostly for what we're doing. Some analysts use 52 weeks of weekly returns. Bloomberg uses monthly returns. I believe Value Line uses weekly returns. So here's how you calculated it. You added, you lined them up, and you ran a regression. This is an annual regression, so you can see it's not going to be as, there aren't as many points on the regression line. So the actual return is in blue, the predicted return is in red. And what OLS does, or ordinary least squares regression, is it minimizes the difference between these points. So it finds the line of best fit that minimizes the difference between the observation and its predicted value. So the beta for this stock is 0.83, and we talked about this in the pre-lecture. The R squared is 0.354 or 355. We don't really pay that much attention to R squared. Actually, we should be looking at adjusted R squared, but we don't pay that much attention to R squared. We should. This indicates that the R squared indicates that 27.4% of the variance in the independent variable, which is the return on the stock, is explained by changes in the return on the market. That's not a ton, but for economic data, it's pretty big R squared. The p-value indicates that with 93.1% confidence, we can conclude that the coefficient on the market return is significantly different from 0. It's not 0. Company betas, I meant to take this out. It's not from lecture 6. It's from previous lecture that we did. I gave you some expected returns and standard deviations when we were talking about risk. Now we've got the betas of these stocks, so we can see that this one is a negative beta return stock, and you can kind of infer that that would be the case because this is a collection agency ostensibly. It's made up data for a collection agency. This is a high-tech company. The high-tech company will have a higher beta. We'll talk about that in a minute because its systematic risk is higher. U.S. Rubber is sort of a defensive stock. It moves somewhat inversely, but not as inversely as collection, so it doesn't move completely with the market because when tires wear out, people buy new tires instead of new cars is sort of the theory. And of course the beta of the index is 1 because you're running a regression of something on itself, and of course the slope of the line is going to be 1. The beta of the T-bill is 0 because the T-bill is guaranteed return. You're always going to get 8%, or in this case that's really, really high, but you're always going to get the same return. So this expected return is equal to the actual return, and there's no standard deviation. you're guaranteed. Okay, so here's what that looks like if you plot it. Okay, so this is the return on the market. This is the return on the security. And the beta of high tech is 1.29, meaning the return on high tech, which is this, right, is more sensitive to changes in the return on the market than the return on US rubber, which has a beta of 0.68. So a beta of less than 1 indicates the security is less volatile than the market. A beta of 1 indicates the security has average volatility, and a beta greater than 1 indicates the security is more volatile than the market. So this is the calculation of beta. If you wanted to directly calculate it, you would take the covariance of the securities returns divided by the variance of the market returns. You have to be a little bit careful about doing that because of we used population standard deviation, so you have to make sure that you use a population covariance, which we did not do. So portfolio betas, this is the cool thing about beta, or one of the cool things about beta, is that a portfolio beta is the weighted average of the beta of the individual securities, betas of the individual securities. So unlike a standard deviation, the beta of the portfolio is equal to the weighted average of the securities betas. And of course the beta of the standard deviation of the portfolio is not equal to the weighted average of the standard deviations of the assets in the portfolio, because as you discovered in 3318 and also in your project, you have to include the covariances in there, or the correlation coefficients. So the beta for a portfolio with 60% high tech and 40% collections is 0.43. Okay. We usually use betas to when we're looking at portfolios. We can look at the beta of individual security. They're not necessarily good estimators of future risk, but they will tell us how much risk that security, adding that security to a portfolio, will add to the portfolio. So how much risk will adding that security add to the risk of the portfolio altogether?